Our lesson on 7.4 is going to talk about functions and their inverses. So first, let's talk about our 5 concepts of inverses that we need to know. First, you need to switch the x and y if you're going to find the inverse. And that's the basic idea for all the following concepts too. So since we switched the x and the y, that means the domain and the range are also going to switch. Now this one's kind of unique. If you graph an inverse, and then you graph the original as well on the same graph, you're going to notice that they are reflections over the line y equals x. And y equals x would be a diagonal line that goes through the origin with a slope of 1. The inverse is a function if the original passes the horizontal line test. We'll talk about that a little later. And then the composition f of g of x and g of f of x both give a result of x. So to say both give, sorry. Typo. Moving on. So first, if our function is just given to us in a table format like this, the relation I should say, then all we have to do to find the inverse is to switch the x and y. So our new x's are going to be our old y, so I'm just going to write them up here in the x's. 4, 2, 0, -2, and -4. And the y's are -2, -1, 0, 1, and 2. Okay, that was easy enough. Now if I give it to you in function notation, y equals 2x minus 4, our first step is to switch our x and y. So x equals 2y minus 4. Well, I've never seen something in this sort of a format when I had to try to give it in simplified form, so what we're going to have to do now is solve for the y, isolate the y. The first thing I'm going to do is I'm going to add the 4 to both sides, and when I do that I end up with x plus 4 equals 2y, and then my last step to get y by itself would be to divide everybody by a 2. Now it's important, especially when we're working with linear functions, to divide everybody individually by a 2. So when I do that, I end up with y equals x over 2 is really a 1/2 x, and then 4 over 2 is a plus 2. And there's the inverse function. Now sometimes, instead of saying y equals, they'll write it as f to the -1 of x equals. And then they would have written the rest of the function. So just notice that the f to the -1 of x is another notation for inverse. Okay, we're going to do the same thing on number 3. Switch our x and y. So x equals -2/3 y plus 6. And now if I'm trying to solve for y, the first thing I'm going to do is subtract the 6 over. So we get x minus 6 equals -2/3 y. And then to get rid of a -2/3 coefficient, I'm going to multiply everybody by the reciprocal, which is a -3/2. And I'm going to do the same thing to the left-hand side. And I notice I put parentheses around the x minus 6 so I don't forget to multiply everybody. I'm going to kind of flip this function around and write y equals on the left-hand side. Now if I go ahead and distribute the -3/2, we get -3/2 x plus, let's see, plus a 9. And there's your inverse function. Again, instead of y, they could have said f to the -1 of x equals. So just notice that notation does mean the same thing. Okay, number 4. We're going to switch our x and y. So x equals 2y squared plus 8. Okay, first thing I'm going to do to solve for y, is to subtract the 8. So we have x minus 8 equals 2y squared. Now because this is no longer going to be a linear function, I'm not so interested in simplifying all the way. I'm just going to kind of make this as clean as possible. So the next thing I'm going to do is divide by 2. And I'm going to go ahead and divide everybody by a 2 like that with a big fraction bar. So right now I have y squared equals quantity x minus 8 all divided by 2. And then the last thing I would do to get y by itself would be to square root both sides. Now since there were no restrictions given to us in the original problem, technically I should write y equals plus and minus the square root of x minus 8 over 2. Now later on we'll see examples of where they give you restrictions on the function, domain restrictions, and you'll see what I mean in a little bit. So number 5, we're going to switch the x and y. X equals 2/5 y minus 4/5. Now the first thing I notice is we've got some fractions, and I'm not so excited about having these fractions. So if you would like to multiply everything by a 5 at this point, you sure could. And I'm going to go ahead and do that. So if I multiply everything by a 5, I end up with 5x equals 2y minus 4. And now I'm just going to get y by itself. So I'm going to add the 4. 5x plus 4 equals 2y. And then if I divide everybody by a 2, This is linear, so I'm going to go ahead and simplify it. We have 5/2 x plus 2. And there's your inverse. All right, moving along. This is one of the properties, I think it was property number 3 in that box at the top of your notes that said the inverse is a function if the original passes the horizontal line test. Well, we've seen what's called the vertical line test. That tells you if a relation is a function. So what I've given you here are the original functions. I don't even tell you what the inverse looks like, but just knowing what the original looks like, you can tell me whether the inverse is a function. So the horizontal line test is like the vertical line test, except we're going to draw horizontal lines. So draw a bunch of horizontal lines, and just like with the horizontal line test, just like with the vertical line test, the horizontal lines can only touch the function once, or the relation once. So since the original, and this is the original here, passes the horizontal line test, that means that the inverse is a function. So off the top of your head, you might not really know what the inverse looks like. He's just going to be a parabola, by the way. But without knowing that, and only knowing what his inverse buddy, or original buddy, looks like, I can tell that the inverse would be a function. Now here on number 7, you can tell pretty quickly that this guy's going to fail the horizontal line test. So since the original fails the horizontal line test, this means that the inverse is not a function. And I don't mind if you abbreviate. Okay, and then number 8, draw a bunch of horizontal lines in. Whoops. And you see that on that example, the original passes the horizontal line test. And since he passes the horizontal line test, that means that the inverse is a function. Now, the horizontal line test does not speak of the original, of whether the original is a function or not. You would still have to do the vertical line test on the original to determine if he's a function. For example, number 6 here, number 6 fails the vertical line test, so the original is not a function, but because of the horizontal line test, we know that his inverse would be a function. So you never know. You got to think about it both ways. Okay, the last property that was in that box says the composition of f of g of x and g of f of x both give a result of x. So they used a little bit of funky notation here. They said f and then f to the -1. You can change that f to the -1. Instead of being inverse notation, you can change it to g if you'd like. So what we're going to have to show, and remember f of g of x can also be written as fog, and g of f of x can be written as goth. We have to show both of those things. Now this is kind of like a proof in geometry. Yes, you have to show it. So we're going to start with fog, and I'm going to say that the g is the blue function. I like to color code these, it helps my brain, and f is the red function. So when I start with f of g of x, I start with the f, which is 2 times x minus 4, and I took the x out, and I'm putting the g inside of where the x was. Remember, this was composition from a previous section. And now we're going to simplify. So I'm going to go ahead and simplify that. I end up with x plus 4 minus 4, and sure enough, that gives me an x. So once I get that, show a little x equals x with a check mark. Now, this should always come out true if these are inverses, but you have to show me the work. It's just like a proof in geometry. You can't skip the step. Now you got to go the other way. G of f. So we're going to start with g, which is 1/2 x plus 2, but in place of the x, we're going to write 2x minus 4. Oh, excuse me. And then we're going to simplify. So let's see, we get x minus 2 plus 2, and those cancel out, the -2 and the plus 2, to give you an x. So yes, these are inverses. And you have to show all of that work. Okay, let's go the other way on number 10. Here's g, and here's f. And we're going to start with fog, f of g. So f of g says, start with f, which is 2 times x plus 3. And we're going to put the g inside of it. Now I can already tell that this is not going to work out. When I go to distribute the 2, I end up with 10x minus 4 plus 3. And since you can tell that f of g is not going to give you just a plain old x on the end, I can stop here and I can say that these are not inverses. There's no point in going to try to prove g of f, because if f of g doesn't work, this can't be a set of inverses. Okay, number 11. Again, if you would like to change the f to the negative 1 to say g, that's fine. So we're going to start with f of g. So f of g says 5 times x plus 20, and then in place of that x, we're going to put g, so the 1/5 x minus 4. Okay, when I distribute that, I'm going to run out of room here. I'm going to end up with x minus 20 plus 20, and that leaves me with just an x. Okay, we're going to go the other way now. G of f. So g is 1/5 x minus 4, and to plug in the f, we get 5x plus 20 in there. Distribute the 1/5, so you get x plus 4, and there's still a minus 4, and that gives you x. So this is our proof that these are inverses. Let's try number 12 now. F of g. F says x to the 3rd power plus 5. Well, what goes inside of the x is the cube root of x minus 5. Now remember, the cube root and the cubed power are just going to cancel each other out, and that leaves you with x minus 5 and then a plus 5, and sure enough, that gives us our x. Now let's go the other way around, g of f. So g is the cube root, and instead of x minus 5, we're supposed to put the f in place of the x, so x to the 3rd plus 5 minus 5. So the plus 5 and the minus 5 cancel, and you get a cube root of x to the 3rd, which leaves us with just an x. So again, we've proven that those are inverses. Okay, number 13 says find the inverse of a function f of x equals x squared for x greater than or equal to 0, and then why does this only work when x is greater than or equal to 0? So let's talk about the original function. Remember, f of x is really just y. So to find the inverse, we would first switch the x and y. So x equals y squared. And then if I wanted to solve for y, I would simply square root both sides. And then when I flip it around, I end up with y equals the square root of x. Or remember, I could also say f to the negative 1 of x equals the square root of x. Now notice on this example, I did not put a positive or negative because they gave me that domain restriction right here. The x has to be greater than or equal to 0. And if you think about your inverse and taking the square root of whatever x is, typically we can't take the square root of negative numbers. We can only take the square root of positive numbers. So because they gave me a domain restriction, I'm just going to leave this as the square root of x instead of saying plus and minus the square root of x. So I won't really give you anything that sneaky here in Algebra 2, but you will run into that in college algebra. So find the inverse of f of x equals 2x to the 3rd plus 1. So again, f of x is really just y. So the first thing we're going to do is switch our x and y around. Whoops, that was not a y. Try again. 2y to the 3rd plus 1. Okay, again, it's not linear, so I'm not going to work too hard to simplify this. I'm just going to do the best I can. I'm going to subtract the 1. So I end up with x minus 1 equals 2y to the 3rd. And then I'm going to divide both sides by 2. Now, notice I'm going to use a big fraction bar again this time. So we have y to the 3rd equals quantity x minus 1 over 2. And then the last thing I'm going to do is cube root both sides. Now, you don't have to worry about plus or minus because remember that only works for even roots and this is an odd root. So y equals, the cube root of x minus 1 quantity over 2. And that is your inverse. And then explain how to use the horizontal line test if an inverse relation is an inverse function. So remember what we did is we had a picture of the original. So our explanation here is that if the original graph passes the horizontal line test, then that meant that the inverse is a function. As simple as that. And describe how the graph of a relation and the graph of an inverse are related. Well, the most basic explanation here is that the x's and the y's are switched. And because the x's and y's are switched, that means a couple of different things. First of all, that means that the domain and the ranges are switched. So the domain of the original is now the range of the new guy, the inverse. And then something we didn't really see an example of, but we could easily prove on a calculator, is that they are reflections over the line y equals x. So what that means is if I had a graph, and I'm going to try my best here to graph, whoops, there's the line y equals x. So if I had a graph that looked like this, for instance, his inverse would be his reflection across that line. So his inverse would actually look like this, a reflection across the line y equals x. So you could typically find whether functions are inverses or not if you look at their graphs and you think about reflecting over the line y equals x. Okay, the steps for finding inverse. First, we're going to switch the x and y. And once you switch the x and y, then your last task is to solve for y. And if you want to be really fancy, instead of writing y equals at the end, you could write that f to the -1 of x. That concludes our lesson on 7.4.